Yeah. Okay. Sorry about this. We continue. So actually, what I want to say that this play the role of cylinder. This one, the role of cylinder. If I have some object in A, some object. Okay, let me place this. If I have some object, and this will be a cylinder in the sense of in the model category. What we have, which fact? So let me write the facts we have. Actually, if first of all, if A is a cofibrant, then this map this map actually that induced from this map from delta 1 to delta 0, the unique map from this to this map will be weak equivalent. Okay. The other fact, so we need this, like the cylinder is equivalent to this, right? We know this actually that we need. And the other thing that if I take this, but actually this is the same as to take this with the 0, you know, with delta 0, and then we take this map to, again, that it's coming from this too. Like from the union of this, there is unique map, there is a map to this, the inclusion. So this map is the cofibration. Okay, cofibration. The other thing that the composition of these maps, like if I compose what I have to compose, first of all this and then this, like 2 and then 1, right? This map and then 1, the map in 1, then this equal to the identity, like where it's from here will be to here, right? So it's equal to this map. So it's exactly to say that this is a cylinder in this model category. Why I want to tell this? Because now we can back to here and show why every 2 lifting, if I have 2 liftings here, then is homotopic. Actually homotopic under A and something like that. Okay, let's say we prove that this is homotopic, and this is very good properties that show also the relation with the simplicial structure. Okay, let me back to this because we don't have now the other side. Let me back to this, and let's say that we have here, we have this map. Actually, what we have just that this map is in this case, like when one of them are like this or this are trivial, so this map will be trivial Kan fibration. So this is what we start with. Let me just write this map. We have this diagram and this diagram, and we know that this map is a map from, I forget this map, from is a Kan fibration in the world of simplicial sets. Now, what if we have 2 here, 2 lifting? It's mean like I have 2 here in the 0 place. Okay, let me write here again. This is the 0 place of this. The 0 place is exactly just map. This is just Cx, Cbx. We have a map to here, see what now the 0 place in here. The 0 place in here will be Cby, Cax, Cay. And now we have the 1 place. What we know that we have the 1 place. I need this because I want to do something here. I want something here, homotopy between these 2. So it's going, I have, try this. I have here two, like let's call F and G. I have here F and G. Two of them are extension. So two of them going to this SK here. Or KS. Yeah. KS is here. So both of them, actually F going to this and G going to this. Okay. And here is the one level. Like the one level, actually what we said before, that this will be this one. Right? And here the one level of this, okay, the same, something like this. So I want to prove that there is something here that hit this two, and this will be homotopy in the sense of model categories. Why? In the sense of model categories, not just homotopy in the sense of simplicial, like equivalence, homotopy in the sense of the simplicial enrichment. No, in the sense of model category, because what we showed here, okay, that this is cylinder. So what we have actually, we can take, we use the property, right? Because we have, what I have this going 2 to 1, and I can choose, I can choose here the homotopy for y, it's just the degeneracy of this. It's here, some digit, it's 0. This will hit this, d0 of this will be this, and d1 of this will be this, right? If I take the degeneracy. And then because actually of the property that if I have two, what is the important property to be trivial vibration, if I have some map, CD, let's call it. See, maybe it's not good because I use C to something, anything like XY I have, anything, okay, sorry, trivial vibration. Then if I have here the homotopy between like 2 points here in X, then I can, because this is inclusion, then I can extend this. So what it's mean? It's mean like if I have two point here, 0 simplex, that the image have homotopy. The image homotopic, then also there was homotopy from the beginning here, right? They have homotopy from the beginning because of this lifting. Even I don't use this lifting, but it's important to say something about this homotopy. But let's do this. So actually, because this actually the image of this are homotopic here, have homotopy for this, because it's unique. So it's easy to take homotopy for this degeneracy. The image of to this, so this have homotopy here. Okay, so this is exactly, I have H here, which is homotopy, that D0 of this is this, D1 of this is this. So this actually tell us, and we say that it's not like this, it's more, it's not just this, sorry, it's more, because one can ask what is the, if I have here homotopy and I have another homotopy, what is the relation between them? And yeah, in this structure, we have all these connections. Okay, that is for this. And now let me say the last fact that appear in the third paper of this series of paper, 3 paper, Dwyer-Kan. So the fact that if we have simplicial model category like this, and we explain what is simplicial model category, then locally is the same. Okay, let me maybe say this and then I can explain. So theorem, say this is important. The theorem say the following. I didn't wrote it, the theorem, so I have to remember what exactly. But yeah, this is actually what if given simplicial model category, not just model categories that have simplicial structure, and with this axiom, what we say. C. Then actually we can do here L C for the right. We can do the hammock localization for this. the Dwyer-Kan localization. And what the theorem tell me that there is Dwyer, if we take, just a minute, if we take the, I'm just confused where I have to take the cofiber. If we take this to be C and F, the cofibration and fibration, okay, here, and we take the Dwyer-Kan of this will be equivalent, Dwyer-Kan equivalent, we mean here, because this is simplicial category. As a simplicial category, this will be equivalent to C, okay? The C at the simplicial category, okay? As Dwyer-Kan equivalence. I want to be sure, just if you wait a minute, I want to be sure to something in the theorems that I maybe forgot, so just a minute. Yeah, so yeah, no, exactly. Because this actually, yeah, exactly. This actually will be the same as this, because we say this. So why we didn't take this? So it's here actually, no, it's here. This is a mistake. No, if we take the simplicial category, so even it's better to say like this. See what I mean by this? Just a simplicial category. I mean, just a simplicial category. Without we forget about the model category, but we take the object, just the fibrant and cofibrant. Then we have Dwyer equivalence to the Dwyer-Kan localization, the hammock localization. We have Dwyer-Kan equivalence. This is the big theorem they have. So it's not tell that, by the way, that the localization, it's by itself a simplicial model category. For no, it's just when we forget about the model category. Okay, we take the equivalence, we build this, and we forget here about the model category. But of course, there is connection, too much connection between the model category structure and the simplicial category here. And even we take here just a cofibrant and fibrant object, then we have Dwyer-Kan equivalence between these two categories. Okay, but here we need also. Sorry. Here we need also. Yeah, because it needs to be the same object. Okay, this is actually the important theorem they have, and that's it. Thank you.